Hello everyone, I am Dr. Tanmoy Biswas. I welcome you all in my channel TanmoyChem. Today's topic of discussion is on MCQ and the question is in front of you. In which case the Grignard reagent preparation is most difficult? Actually, I have provided 4 haloarenes and from there we will prepare the Grignard reagent. So which case it is difficult? I request everyone please pause the video, try by yourself and whatever answer you get, please write in the comment box along with few words as explanation. I believe you have tried, so let's start. By the way, student, this question apparently may be very easy, but when I shall discuss this, I'll explain lots of interesting information and logic in this video. So from conceptual clarity, this video is very important. Now, let's start. So, Grignard reagent preparation, the first point. So, let's learn a little bit about the basic concept about it. So now if you look at magnesium, this magnesium releases 2 electron and became magnesium 2 plus. And these 2 electron actually responsible for the breakage of this carbon halogen bond. Because if you look at in this carbon halogen bond, this carbon is delta positive, halogen is delta negative. But when these 2 electrons are accepted in this bond, means this carbon atom, carbon became delta negative, X became delta negative. So you may consider it's like a pH minus Mg2 plus and X minus. By the way, Grignard reagents carbon magnesium bond nearly 30 to 40% polar, but it is a covalent bond. So it's a very polar covalent bond. So now if you look at, I'm talking halogen, means chlorine, fluorine, bromine, iodine. So actually this bond strength between the carbon halogen is one of the important factor here during the preparation of Grignard. Means Grignard is releasing 2 electron, that's fine, but these 2 electron, how can it break this 2 bond? Now, so we need to understand a little bit about the bond strength of different CX bond. Logic is that if the bond is weaker, that will be broken very easily, so Grignard reagent will be prepared very easily. So let's look at the second point, the bond strength versus partial double bond character in these haloarenes. How? So if you look at this fluorobenzene, so this fluorine lone pair can be donated inside the benzene nucleus and resulted in this canonical form. By the way, other canonical form also possible, so it will come here, it will go there, means you can expect that, okay, double bond F having plus charge. By the way, 2 lone pairs still there. Now negative charge is here. In the next canonical form, it will push, it will go. So from here you can also expect that, okay, there is F plus, this is negative charge. So from there you can clearly understand that the negative charge moves around the benzene ring, and during this process you can clearly see that there is a carbon fluorine partial double bond. So in this canonical form there is double bond, but if you look at overall there is a single bond, and this canonical form has more contribution. So consequently you can say there is actually a partial double bond character in all haloarenes. Now if you look at chlorine case, similar partial double bond character. In case of bromine, similar way, it's a double bond. Iodine, this is. Now partial double bond character exists for everyone, but question, in which case the extent is higher, or in which case the stabilization is higher? Remember student, when during any kind of overlap, 2 factor actually very important. One is symmetry matching, another is actually energy matching. So if energy and symmetry both matches, bond became stronger. So if you look at in case of fluorine, actually all cases carbon is fixed, this phenyl ring part. So fluorine second row element, carbon is second row element. Chlorine third row element, carbon second row element. Bromine fourth row element, carbon second row element. Iodine fifth row element, carbon second row element. Now you can understand from fluorine to iodine, if you go size increases, so energy increases. Symmetry is there, but energy increases, and consequently the overlap get reduced. So if you go from this to this, so overlap of the orbital get reduced. So if overlap reduced, you can say bond strength reduce. So if the bond strength reduce, you can say easily it could be broken. So from this thing we can clearly understand, okay, these will be very easily broken, and which of the molecule is most difficult to break? Obviously option A, fluorobenzene. But one point I also want to share with you, you may think, sir, resonance, is it really that much easier in these aromatic halides? No. Aromatic halides are ortho and para orienting but deactivating. Why? Because in this case the electron donation, I mean plus R effect, is less dominant compared to the minus I effect, means sigma withdrawing by the halogen. Why? Because halogen are very high electronegative atom, so they can donate electron density in the benzene ring, but compared to their donation, their withdrawing through the sigma bond is higher. So now I want to give you an additional information which is the proof of the concept whatever I have taught you. Now one question, if X equal to Cl versus Br, so I am talking here about chlorobenzene versus bromobenzene. Now if you look at, so I can say clearly the carbon chlorine bond is stronger than carbon bromine bond because the partial double bond character in this chlorobenzene is more compared to bromobenzene. Why? Because chlorine is third row element, means these lone pairs are in the 3p orbital, whereas in bromine 4p orbital. So 2p 4p overlap, I mean carbon bromine orbital overlap is lesser, so this bond is weaker. Proof of the statement, if you want to get Grignard reagent from this chlorine and obviously metallic magnesium anhydrous solvent etc., if you take simple diethyl ether, it's very difficult because slight heating needed. Why? Because the bond is stronger, so if you want to break a stronger bond, you need to supply energy in the form of heating. So that's why the preferred solvent is generally used THF, tetrahydrofuran. So why? Because it's a cyclic ether and its boiling point is slightly higher compared to the diethyl ether. So if you use this tetrahydrofuran as a solvent, you can supply slight amount of extra energy in the form of heat such that you can prepare your Grignard reagent very efficiently from chlorobenzene. But if you look at bromobenzene, you can do in the diethyl ether also. That much amount of heating not needed. Now if you say, sir, if I take THF, that will be no problem. But for chlorobenzene, THF presence is better because some amount of heating is needed in order to break this carbon chlorine bond. Why? Because stronger bond due to partial double bond character. Remember, very important. They can give another MCQ, which of the solvent is best for preparation of Grignard reagent from chlorobenzene to the phenyl magnesium chloride, this reaction. So they give 4 options. For example, one is diethyl ether, another is THF, another maybe hexane, another maybe toluene. So we understand, we know that these hexane, toluene, hydrocarbon solvent are not good for diethyl Grignard reagent preparation because these oxygen lone pair coordinates to the central magnesium atom, actually 2 ether molecule, 2 oxygen, such that they can stabilize this ether molecule. That is the reason why we use ether or THF as a solvent during this Grignard reagent preparation. So that could be another MCQ. So this information is very important, very helpful, and nobody knows which question may come. And here one thing, anhydrous solvent. Why anhydrous solvent? Because this Grignard reagent carbon is delta negative, magnesium delta positive, so nearly 30 to 4% ionic character present in this carbon magnesium bond. So if you look at water, anhydrous means it may have moisture, the opposite thing. So this is delta plus, so these can react with this H plus and it can produce benzene. So that could be the side reaction, that's a wastage of reagent. In order to prevent that wastage, actually anhydrous solvent like anhydrous ether, anhydrous THF are taken for this reaction. Now let's go back to our main question. In which case Grignard reagent preparation is most difficult? Answer is fluorobenzene. Why? Because the partial double bond character is maximum, the bond strength is maximum. Not only that, remember the carbon fluorine covalent bond is very stronger. One of the very important example of Teflon, polytetrafluoroethylene, this polymer we use on non-stick cookware as a coating. This polymer is significantly stable that it doesn't undergo degradation very easily during the cooking also. So this proves that okay, this CF bond is stronger. Not only that, here partial double bond character exists. So this phenyl magnesium fluoride preparation is significantly difficult. But I have already discussed a dedicated lecture on preparation of Grignard reagent from such kind of fluoro compounds. So you may visit if you want to learn, and I have already uploaded another dedicated lecture regarding Teflon, so you may visit. It's a very interesting polymer. So this is a very interesting discussion. I believe this video will be useful. But by the way, if you get this question in your exam hall less than 30 seconds, how can you solve? one option. Remember, carbon fluorine bond is very stronger. Means if you look at all carbon halogen, aliphatic, aromatic, both case it is applicable. So stronger bond, difficult to break, Grignard reagent preparation will be most difficult in this case. And second thing you should remember, if you look at the Plasar effect is maximum, means possible donation for fluorobenzene. Why? Because second row element orbital overlap is better, so this back donation or Plasar effect is better. So this is the overall discussion. I believe this video may be useful, and if you really consider the content of my channel is worthy, then please help this channel to grow. And if you have any doubt regarding the logo of my channel, please read this part, your doubt will be clear. So see you in my next video. Bye bye.